So your first step is to think about what kind of energy those two problems are talking about, and if you know any equations for those energies. I did find a teacher's email. Oh, you did? Yeah. Okay. No. Everybody's gone. So sad. Where'd they all go? Together because we have a whole bunch of notes to take today. So have your do now sheet out, and we're going to work on these two things together. You might want to have your notes from yesterday with you also. Wyatt, I'm sorry I didn't get to you this morning. Well, oh, Bandy, are you okay? You still,
I'm good.
Still dying? Well, I'll give you one. Do you want cartoons or just plain? Plain? All right. So ladies and gentlemen, take a look at that do now. Take a look at problem number 1. What does problem number 1 say? Wyatt, I'm helping you out here. Go ahead and read that problem.
Calculate the energy of a 12.5 kilogram rock sitting at the top of a 35-meter tall cliff.
Great job reading that problem, Wyatt. You got all the vocabulary words exactly correct. So if an object is sitting at the top of a cliff, is the object moving? Yes or no, ladies and gentlemen? With a little bit more enthusiasm, I know it's early in the morning. Is the object moving, yes or no?
No.
No, that object is not moving. So does it have any kinetic energy, yes or no? No, but it has another type of energy because it's at the top of a cliff. What kind of energy do things above the ground have? Think about it. What kind of energy is that, ladies and gentlemen?
Gravitational.
Ooh, listen to those intense vocabulary words from Jet. Jet, tell us those amazing words one more time.
Gravitational potential energy.
Ooh, listen to those smart words. Okay, ladies and gentlemen, let's all be smart together. What kind of energy does an object sitting at the top of the cliff have? Everybody ready to go?
Gravitational potential energy.
Excellent job with those vocabulary words. And we're going to abbreviate all of those crazy words with the variable UG. How do we abbreviate gravitational potential energy, everybody?
UG.
You got it. Now we need to write the equation for gravitational potential energy. The equation for gravitational potential energy is mgh. What equation do we know for gravitational potential energy, everybody?
MGH.
mgh. Wonderful. What does the M in mgh stand for? What vocabulary word is that, ladies and gentlemen? Wonderful. And what does G stand for, ladies and gentlemen? Yeah, you got it. Well, it's the acceleration due to gravity. So one more time, what does G stand for, ladies and gentlemen?
Acceleration due to gravity.
Oh, smart children. And what does the H stand for, smart children?
Height.
Height. Okay. Do we know the mass of the object? Yes. What is the mass of this object, Ariana? That's the height of the object. So we'll need that number in just a second. Let's try it for the mass this time. What's the mass of the object, Ariana? You got it. 12.5 kilograms. Great job putting the units in there, smart lady. And we all know G. It's going to be a positive version this time. So what is G? The number with units, always. Everybody. That was most of you. All right, I will get everybody for this next one. 9.81 meters per second squared. And the height of the cliff. What is the height of this cliff, Eric? 35 meters. Great job answering quickly with the units and everything there, Eric. 35 meters. And now we're going to very, very carefully multiplicate to get the potential energy. Go ahead, ready to do that. Matthew, I'm glad you're here. That's great. We're just working on our do now. All right, so when you multiply so very carefully, what do you get for the gravitational potential energy here, Connor? Oh, before you tell me your answer, I know it was right on the tip of your tongue and I just interrupted you, I'm sorry. Before Connor tells me the answer, what are the units of energy, ladies and gentlemen?
Joule.
Woo, good memory. Okay, Connor, one more time, go for it. 4,290 what? 2 Jules. Nice. Raise your hand if you got that answer. Sweet. Success. High five to your neighbor. Air fives for Connor. Connor, you must receive your air fives with a psh. Everyone go psh at Connor. Woo. Okay. Now apologize to your neighbor for spitting on them a little bit. Okay. Let's keep going. Now we've got part 2. What does part 2 say here, Michelle? Moving with the speed of 25 meters per second. Great job reading that problem correctly, Michelle. If an object is moving, what kind of energy does it have, Megan? Oh, good job with that quick vocabulary. What kind of energy does a moving object have, ladies and gentlemen? Kinetic. So we need the abbreviation for kinetic energy. What's that abbreviation, Kia? K-E. And nice, good job with that abbreviation, Kia. So what is the equation for kinetic energy? Everybody. You got it. That's a very important equation. Let's get that one all together. So one more time, when I ask you for kinetic energy, all you need to tell me is 1/2 mv squared. What is the equation for kinetic energy, everybody?
1/2 mv squared.
Brilliant. So we've got the 1/2 out front. We're going to remember that. What does the M stand for, ladies and gentlemen? Mass. Do I know the mass of this rock, Eli? What is the mass? Oh, is it a rock? Yeah, it is a rock. 1/2. What is the mass of that rock, sir? 12.5 kilograms. Nice quick answer with the units there, sir. And what is the V? What vocabulary word in physics class do you know that starts with a V? Caitlin? Velocity. Nice job with that V. Vocabulary V word. And what is the velocity of this rock here, Lawrence? Ooh, nice quick answer with the units and everything, sir. 25 meters per second. And what are you going to remember to do to this velocity, ladies and gentlemen? Square it. Okay. So go ahead and calculate. After you calculate and check your neighbor, make sure they remember the 1/2. Make sure they remember to square it. If they've remembered all these things, you may high five them in celebration. Oh, Ariana, what's up?
How do you plug in square?
C. Right there. You got it, Matthew? Man, you're catching up quick. Well done. Nice work. Well, it's an exciting day today of physics. We're do some cool lessons today. I'm very excited. I'm always excited. All right, here we go. What did you calculate for the kinetic energy? Did you remember the 1/2? Say yes. Did you remember to square your velocity? Say yes. I believe you. You are all very smart physicists. And what are the units of energy, ladies and gentlemen? Joules. Okay, so putting it all together, what did you calculate for the kinetic energy of this rock that's moving super fast, Jordan? 3,906 joules. Raise your hand. You got that same number? Yes, you may congratulate your neighbor. Say, good job, neighbor, remembering to include the 1/2 and the square. Go ahead, congratulate your neighbor. All right. Excellent. All right. So far, you can go ahead and transition to taking notes. We've seen 2 types of energy. Energy can take different forms. If it is an object that's moving, or if it's an object that's sitting at the top of a cliff, it has different forms. There's one more form of energy we're going to learn about today, and that is elastic potential energy. All right, so yesterday we learned about gravitational potential energy. Today we're going to learn about elastic potential energy. So we can maybe predict what the variable for elastic potential energy is going to look like. So if it is any kind of potential energy, I'm going to use the U. So is this a potential energy, ladies and gentlemen? Yes. So how am I going to start the variable for elastic potential energy? With what letter, ladies and gentlemen? U. Listen to you, smart physicists. Good job. And I'm going to have a U. Elastic potential energy is going to be the energy in a spring or some kind of elastic thing like a rubber band. So it's going to be U subscript SP for spring or elastic potential energy. And this is going to be the energy stored. Hang on just a second, Libby. The energy stored in a spring that is extended or compressed past equilibrium. Nice job with those notes. Libby, what's up? You can ask me a question while you're taking notes.
Oh, I was just gonna ask you.
I sure do. Do you want plain or cartoons? Okay. I'll pick the cartoon for you. I just got some Rudolph Band-Aids. I'll get one for you. Be in the Target dollar aisle, man. We get in trouble. There you go. All right, so ladies and gentlemen, elastic potential energy is the energy stored in what kind of object? A spring. One more time. Elastic potential energy is stored in what kind of object?
Spring.
A spring. You got it. And now here's the equation for elastic potential energy. You guys ready? Here we go. USP is equal to 1/2 K x squared. That kind of looks like the equation for another type of energy we know. What kind of energy do we know that has a formula kind of like that? What type of energy do we have here, ladies and gentlemen? Kinetic energy. So different kinds of energy look similar. Well, that seems reasonable. Okay, let's talk about what these variables are. The K is the spring constant. And it's a measure of how stiff the spring is. So let's talk about that spring constant with a couple of these springs up here. All right, Eli and Wyatt, I'm going to need your observational skills. Are you guys ready to observate? Is your injured finger okay? Are you going to be able to compress the spring? Okay, I think you can handle it. You're going to have to persevere. If you can't, Eli can take over for you, okay? All right, so ladies and gentlemen, I have here 3 different springs. I have spring number 1. Play with spring number 1. So tell me, is that spring particularly difficult to extend or compress, Eli? No, that spring is pretty wiggly. We'll pass these springs around in just a moment so you have a moment to play, some time to play with them. So Eli observates that that spring is pretty wiggly. So if a spring constant is a measure of how stiff it is, Eli, do you predict that that spring has a large or a small spring constant?
Small.
Small. Excellent prediction. So if it has a small spring constant, is the spring easily compressible or difficult to compress? What do you think? Small spring constant, easy or hard to compress that thing? What do you think, ladies and gentlemen? Easy. Yeah, nice observation. Okay, great. So go ahead and pass that one along. Play with that wiggly one. All right. Here you go, sir. Here's spring number 2. Now, you're very strong, Eli. Can you compress that spring?
Yes.
Yeah, you sure can. But how does it compare to that first spring that you were playing with, sir?
It's a lot harder to compress.
It's a lot harder to compress. So do you think that that spring in your hands right there has a larger or a smaller spring constant than the other one?
Much larger.
Much larger. Excellent. Great observation. So larger spring constant, harder to compress. All right, Eli, I'm going to test your strength here. Here's spring number 3. Tell me about that one. What do you observate?
That this one you can't even really compress.
Okay, so excellent observation. What would you say then about the spring constant for that one, sir?
That this one has to be really high.
Really large spring constant. Great observations. Excellent. So ladies and gentlemen, as these springs are going around, we're going to continue to take notes, but I just want you to get a feel for different values of a spring constant. Okay, cool. So the next item in this equation is the x, and the x is going to be the distance the spring is compressed. Or extended, I guess. Awesome. All right. Now, what are you going to remember to put in front of this equation, just like kinetic energy, ladies and gentlemen? 1/2. Remember, what are you going to remember to put in front of the equation? Everybody. You got it. What are you going to remember to do to this x? Everybody.
Square.
Nice. Great. Excellent vocabulary words. Okay, so let's do a quick example problem just with this elastic potential energy, just to see how it works. I'm sure you guys are very, very smart and you can figure it out, but we're going to play with it anyway. So here we go. You might be asked in your homework to calculate. Now remember, when I write down a problem on the board, it's in your best interest to copy down all of the words in the example problem, as well as the work to solve it, because you will very, very likely, hint, hint, wink, wink, see a problem exactly like this in your homework. And it is to your benefit to write down all the words in your notes so that when you get to your homework, you can be successful there, okay? Okay, you can be successful. Calculate the energy stored in a spring with K equals, I don't know, 450 newtons per meter, extended. How far can you, who's got the wiggly spring? Show it, wiggle the spring. Oh, there you go, okay. How far can you extend that spring, Libby? Pretty far, so we'll say like, I don't know, 40 centimeters. That seems reasonable. Nice. Great. Extension of that spring there, Libby. Extended 0.40 meters past equilibrium. All right. So we're asked to calculate the energy in a spring. Well, it's fairly straightforward here, but ladies and gentlemen, we need to pick an equation. Now, there's really only one equation we're going to pick. What equation are you going to pick to calculate the energy in a spring, Eliana? Nice, you got all the variables. Great job, Eliana. Absolutely right. The equation we're going to use is USP equals 1/2 kx squared. Go ahead and read this equation to me. Everybody ready to go?
USP equals 1/2 kx squared.
Nice job with all of those variables, ladies and gentlemen. You got them all. You remember the 1/2. You remember the squared. Great work. What does the k in 1/2 kx squared stand for? You could read just this part. What does the k stand for, ladies and gentlemen? Spring constant. One more time with those vocabulary words. What does the k stand for, everyone? You got it. And what is the spring constant for this particular spring in this example problem, Matthew? Yes, continue with the units, sir. Nice, great job reading those units, Matthew. Very complete. So I've got 1/2 times 450 newtons per meter. And what does the x stand for in a spring problem here, Nayeli? Nice, great job reading all of the parts there of x. And am I given the distance the spring is extended or compressed here? Yes or no, ladies and gentlemen? Yes, what is that distance here, Nayeli?
0.4 meters.
Nice, great job finding that number, reading it correctly with the units and everything. And what are you going to remember to do to that x every single time, everybody? Square it. Okay, you can pretend to be excited. It's okay. I know it's. Oh, good, pretending, Madeline. Well done. So go ahead and use your amazing calculator skills. As soon as you're done calculating, check your neighbor. Make sure that they have remembered the 1/2, that they have remembered to square it, and then congratulate them once they have. Where's your neighbor? Oh, that's sad. I'm sorry. Well, I'll congratulate you. Did you remember to square it? Did you remember the 1/2? Congratulations. Great job remembering to square it in the 1/2, Matthew. Well done. Oh, yes, ma'am. Oh, thank you. Does anybody need to play with these springs still? You got to play with them all? You got the tough one and the slightly squishier one and the really wiggly one? Okay, Matthew, looks like you've done a great job calculating the spring energy. Now, before you tell me this is still an energy, even though it's not kinetic or potential energy, it's still an energy. What are the units of energy always, ladies and gentlemen?
Joules.
Woo, you guys are so smart. Well done. Okay, so Matthew, tell me the energy stored in the spring with units and all that good stuff. 36 joules. Raise your hand if you got that same number. Excellent job. High five your neighbor. Say, good job, neighbor, remembering the 1/2 and the squared. Let's carry on. All right. So we now know of 3 different types of energy. We learned how to calculate the energy of objects in various situations. But here's where we can go with this. Energy can change forms. It can go from gravitational potential energy to kinetic energy. An example of this might be a rock falls off a cliff, or maybe a skydiver. That's a better one. So, raise your hand. Ooh, has anybody in here ever gone skydiving? Ooh, anybody want to go skydiving? Oh man, okay. All right, so you potential skydivers out there, you've probably seen like the YouTube videos. These guys, they start in an airplane really high off the ground, right? So they start and they're high off the ground. What kind of energy do you have if you're above the ground, ladies and gentlemen? Nice job with those vocabulary words. You have gravitational potential energy. What kind of energy do you have if you're above the ground, ladies and gentlemen? Gravitational potential energy. All right. And now, if you jump out of the airplane, do you just stay there? I mean, if you're in like a Wile E. Coyote cartoon and you don't realize you're walking off the cliff, yeah, you just stay there. But that's not how it works in real life. What happens when you jump out of that airplane, Caitlin? Yeah, you fall. So when you're falling, are you moving, ladies and gentlemen? Yes or no? Yeah, you sure are. So what kind of energy do you have if you are moving? Kinetic energy. So skydiving is an example of going from gravitational potential energy to kinetic energy. We can change forms in another way. We could go from kinetic energy to gravitational potential energy. An example that I can think of here is if you're on a roller coaster. Raise your hand if you've ever ridden a roller coaster. Oh man, anybody ever been to anywhere other than like the Elitch's in Denver? Oh, where have you been, Connor?
I've been to a couple different Six Flags, the Disney World, Universal, and Hershey Park, and King's Dominion.
Man, you are well traveled in the land of roller coasters. Where have you been, Libby?
Cedar Point,
Which one?
Northern Ohio.
Me too. I grew up in Ohio. Okay, so the first roller coaster upside down one I ever went on, I was like 8 years old. I was like just tall enough. Oh man, it was great. So, what do you remember the names of any of the roller coasters you went on there?
There's the Top Hill Baxter and the Millennium Force.
Oh, sweet. I haven't been there in quite some time, so I bet it's even better than when I was a kid. Okay, awesome. So, but most of us have ridden on a roller coaster. Now, when you're riding on a roller coaster, once you get past that first hill, there's no engines on it anymore. It's all this energy stuff. So we're going to do some conservation of energy problems here in just a minute with your roller coasters. But when you are on a roller coaster and you get to the bottom of a hill, you get to the bottom of one of those dips, do you just stop there at the bottom of the dip? No, what usually happens there, Tatiana? You go up a hill. Excellent. So when you're at the bottom of the hill, are you moving? Yes. And that kinetic energy is enough to give you more potential energy to get to the top of the hill. So here's an example of a roller coaster. You could also possibly change from spring potential energy to kinetic energy to gravitational potential energy. An example of this, I went to Target last night, got some new toys. Oh my gosh, I'm so excited. Might be, might be a Nerf gun. So, when I pull this thing back, something has clicked into place. What do you think is inside this that clicked into place, ladies and gentlemen?
Spring.
A spring. Excellent. And when I pull this thing back, I have a spring that's either extended or compressed. I can't see in there. I don't really know if it's either. But if I have a spring that is extended or compressed, what kind of energy is contained inside of this thing right now? Spring potential energy. Excellent. And if I pull this trigger, what's going to happen, ladies and gentlemen? It's going to release the spring, and what's going to happen to the projectile? It's going to move. So I went from my spring potential energy, when I pull the trigger, it's moving. Now if I point this thing straight up in the air when I pull the trigger, what's going to happen to the projectile? It's going to go up. And if it's going above the ground, what kind of energy is it gaining, ladies and gentlemen? Gravitational potential energy. Ha! Okay, nobody is excited as I am. You're like, don't shoot me with that thing. Don't fall asleep in my class, or I'm going to have ammo to shoot you down. Ha ha. Okay, so here's what we're going to do. Oh, I'm sorry. Where'd my pen go? In my pocket. A Nerf gun. I had a bunch of these last year, and then when I was gone at the end of the year, they all disappeared. I don't know what happened. Me and Mr. Kegrice used to get in all kinds of battles. I would like arm the kids, and we'd run into his room, and we'd bang, bang, bang. And then it was really awkward because we'd have to like go pick up the ammo. Except most of the times the kids were really nice because I would like go aim for Mr. Kegrice, and then the other kids would give me my ammo back, and then I'd shoot him again, and the other kid was great. It was awesome. Okay, so here's what we're going to do. We're going to look at problems where we're changing from one form of energy to another. And some important things that we need to know before we do that. How you guys doing so far? Taking a lot of notes. It's kind of warm in here, or is it just me? Usually it's freezing in here. Okay. Here we go. Alright, the important thing that we need to know before we can solve these problems is that for any system, total energy is conserved. Conserved. And here's how we can write this. We can say the total energy is going to be all of the possible types of energy added together. So tell me one type of energy that you know of, ladies and gentlemen. Ooh, Caitlin knows of a type of energy. Tell me one type of energy that you know of, ladies and gentlemen. Gravitational. Okay, so total energy might be gravitational potential energy. Tell me another type of energy that you know of, ladies and gentlemen. Kinetic energy. Nice, so I'm going to say plus kinetic energy. And tell me another type of energy, the type that we just learned about today. What's another type of energy you know about, ladies and gentlemen? Spring potential energy. Remember, what is the abbreviation for spring potential energy, Madeline? not weird. Who made that you feel bad? You apologize today.
Sorry.
Okay. It,
So 3 nice things.
You're funny. I'm just kidding. You say 3 nice things about that you. Yeah, that's right. You're nice and swirly, and you have a cool tail on the front. I don't know, and I'll come up with another one later. All right, so total energy is going to be all the types of energy we know about added together. What's up, Eli?
Why don't we use sigma there?
We could, we will eventually, but because we're in general physics, we're just going to add them together. So you're on the right track. Excellent math knowledge and Greek letter knowledge, Eli. Well done. We'll get there eventually, sir. But as far as we're concerned now, this is what you need to know. And when we solve problems like this, we're going to call them conservation of energy problems. And you'll very quickly learn to recognize conservation of energy problems. And if nothing else, if you know how to do nothing else, you will start a conservation of energy problem with the following statement. EI equals EF. What do you think this capital E stands for here, Matthew? Energy. Excellent. What do you think this capital E stands for, ladies and gentlemen?
Energy.
Nice. Brilliant. Great work, physicists. And if I have a conservation of energy problem, this is going to tell me that all of the energy at the beginning of the problem equals all of the energy at the end of the problem. Or energy initial equals energy final. Great. You want to see an example of this? It's going to be great fun. So here's an example of a conservation of energy problem. You guys have been wondering about this purple string, huh? I bet you were. If you weren't, now you are. You still wondering about the purple string, Jordan? Yeah? Okay. All right. I got a mass here. I'm always surprised when it stays up there because it's kind of just like in the ceiling tile. Don't breathe too hard. Okay, ladies and gentlemen, I have here the pendulum of science. So here's what we're going to do. We're going to demonstrate some conservation of energy problems with this pendulum. Now, conservation of energy tells me that all of the energy at the beginning of the problem equals all of the energy at the end of the problem. What does conservation of energy tell me? Think about that statement in your head really fast. All of the energy at the beginning of the problem equals all of the energy at the end of the problem. So what does conservation of energy tell me, everyone?
All the energy.
Listen to you brilliant physicists with all that great vocabulary. Wonderful job. So here's what I can do. I'm a physicist. I can define the beginning and the end of the problem wherever I want. So let's say that I define the beginning of the problem to be right here. And let's say I define the end of the problem to be over there somewhere. Conservation of energy tells me that all of the energy at the beginning of the problem equals all of the energy at the end of the problem. So what kind of energy does this have right now? Let's say that this is the lowest point in the swing. Is my pendulum above the lowest point in its swing? Yes or no?
Yes.
Yes. What kind of energy do things above the ground or the lowest point have, ladies and gentlemen? Yes. So what kind of energy does it have right here, ladies and gentlemen?
Gravitational potential.
And when it gets to the other side, is it going to be able to gain magical energy somewhere? No. So it should have the same amount of gravitational potential energy over there. Does its mass change? No. Does gravity change? No. So its height should also be the same when it gets over there. Now, its height should also be the same when it gets back. Let's hope that physics works. And when I release this thing, it doesn't magically gain energy anywhere. This is why you all get to stay sitting, because if I have smart children release it, some of them like to push it, and that gives it a little extra energy. And I like my teeth and my nose. I've already broken my nose a couple times, not with this, but I don't need to, do that here again. So let's see if physics works. If energy is conserved, then it should just get to this point right here. Ready? You frightened for me? It seems to be more frightening when I put like a TV or some sort of important technology here. My face is not so impressive to you guys. Okay, here we go. You guys ready? Okay, now I'm going to let this go for a while. Now, conservation of energy tells me that this thing should have energy being conserved. It should swing back and forth, reaching the exact same height forever and ever and ever. But physicists, is that going to happen, yes or no?
No.
No, but energy is conserved, so where can some of that energy go? I'll take volunteers here. Where do you think some of that energy is going? Where do you think, Jet?
It dissipates in heat.
In heat? Wonderful, brilliant physics vocabulary. I didn't even have to pull it out of you. So some of this energy goes to heat. I mean, if you take a look at the swinging part up there, it's kind of destroying the tile up there a little bit, which is basically heat. You can't really hear it, but it's making a little bit of wind noise, and so that's any other place that energy goes other than gravitational potential energy, kinetic energy, spring potential energy is going into heat. So let's write down some of these important things. Conservation of energy, some energy is lost to heat. All right, so let's go ahead and see if we can use this pendulum to solve an important example problem in physics class. So something you might be asked on your homework, hint, hint, wink, wink. Now I have to be careful when I navigate through the room. Something you might be asked to do is to calculate the velocity of this pendulum right at the bottom of its swing. So let's go ahead and write down this problem, and we'll practice solving it together. So calculate the velocity of a pendulum at the bottom of its swing. Alright. Okay, ladies and gentlemen, this is our first foray into a conservation of energy problem. But a question I'm going to ask you many, many times in the future is, what kind of problem is this? And you're going to tell me conservation of energy. So, ladies and gentlemen, what kind of problem is this right here on the board right now? What kind of problem is that, everybody?
Conservation.
Brilliant vocabulary words, physicists. And we always start a conservation of energy problem with EI equals EF. How do we always start a conservation of energy problem, everyone?
EI equals EF.
You got it. So that's the first thing you're going to write when you solve these problems. EI equals EF. Oops. EI equals EI. EI, EI, oh, I just want to be a farmer. No, just me? Okay. Farms? I don't know. I don't think I can. Yes, ma'am.
Tyson Davis.
But I need him. Is he going to come back?
He will.
Okay,
yes.
come back soon, Tyson. We'll miss you. Okay, so I started off this problem with EI equals EF. This tells me that all of the energy present at the beginning of the problem equals all of the energy at the end of the problem. Let's go ahead and just write down all the types of energy, and then we can cross out what we don't have. So tell me one type of energy that you know about here, Michelle. Yes, and what are the vocabulary words that go with that? Do you remember?
Gravitational.
Brilliant job. You got the variables and the vocabulary words. Well done. So I might start off with UG. What's another type of energy I could start with here? Diana? KE, and what are the vocabulary words that go with that type? Nice. Brilliant job with those vocabulary words, Diana. Plus KE. Plus another type of energy that I could have at the beginning of this problem, Lawrence. You got it. What are the vocabulary words that go with that type of energy? Yes, excellent job. Great work there, Lawrence. You got the vocabulary words. Elastic potential energy. USP. And I could also have all of these at the end. So I'm going to say initial, 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 and write all of these things with finals. UG final plus KE final plus USP final. Okay, now here's what I'm going to do. I need to figure out where the beginning and the end of this problem is. So the beginning of this problem, I'm going to define as the pendulum being held at rest at some height above 0. So I'm just going to think this in my head. So this is the beginning of the problem right here. And what is this problem asking me to solve for here, Eric? Nice, great job reading that problem, Eric. So the velocity of the pendulum at the bottom of the swing. So I'm going to define this point right here as the end of the problem. So I'm going to consider this the beginning of the problem, and this is the end of the problem. So at the beginning of the problem, ladies and gentlemen, let's figure out what kind of energy that this has. Right now, take a look. Beginning of the problem. Is this pendulum moving? Yes or no? No. Is this pendulum have any springs or rubber bands attached to it? Yes or no? No. But is this pendulum above its lowest point? Yes. So let's think about that as we determine what kind of energy it has. So you told me it was above its lowest point. So what kind of energy does an object above its lowest point have, ladies and gentlemen? Yeah, good job answering that question. I asked it very poorly, but it has gravitational potential energy. At the beginning of the problem, is the object moving? Yes or no? No. So does it have kinetic energy? Yes or no? Nope, so I can cross this out. There it goes. And were there any springs at the beginning of the problem, ladies and gentlemen? Yes or no? Nope, so what can I do with that term? Cross it out. There it is. Okay, So I've got one type of energy present at the beginning of the problem. Let's see if we can determine what kind of energy is present at the end of the problem. So you're going to have to kind of imagine this as like a snapshot. So imagine the pendulum is moving, it's moving, it's moving, it's moving. Right at this very instant where it's at its lowest point, is the object moving? If it was still in the problem. I'm holding it still right now just for demonstration purposes. But in the real problem, would the object be moving right here, yes or no? Yes, it would be moving. So what kind of energy does it have right here, ladies and gentlemen? It definitely has kinetic energy. Can it get any lower than this? No. So does it have any gravitational potential energy right here? No. And are there any springs or rubber bands attached to it right here? No. So what is the only type of energy present at the end of this problem, ladies and gentlemen? Kinetic. What can I do with these other terms? Cross them out. Here they go. Bam, bam. Okay, so I've got a lot of stuff and I've got some things crossed out. I'm going to make my life a little bit nicer and rewrite what I have here. So I've got UGI equals KEF. Well, that's a lot simpler than it started. That's nice. Look kind of scary. Is your eyeball falling out? Good, because I don't want to clean that up. Okay, so let's think about now the equations that I know for these two types of energy. What equation do you know for gravitational potential energy? What type of energy, one more time. What is the equation that you know for gravitational potential energy? Everybody. Yes, that's the variable. Excellent. Just the second half of the equation. What do you know for gravitational potential energy, everybody? MGH. So I'm going to write MGH right here. And what equation do you know for kinetic energy? Just tell me this half of the equation. Ready, go. Brilliant. I heard you nice and loud, Brianna. Well done. 1/2 mv squared. Okay, so I've done a lot of work so far. This is a good stopping point to remember what I'm trying to solve for. What am I trying to solve for here, Jordan? Brilliant job with that vocabulary word. Great. What variable do you see in this equation that might represent velocity, Sally? V. Excellent. So I'm trying to keep track in my head what I'm doing because I'm doing lots of stuff here. I'm trying to solve this equation right here for V. Okay. Do you see any variables present on both sides of the equal sign that I could cancel? What do you see? M. So I have an M present on both sides of the equal sign. I can cross it out. Here it goes. Bam. Bam. Let's rewrite it without those M's. GH equals 1/2 V squared. Okay. Now Sally correctly told me that I'm solving for a V. What is preventing this V squared term from being by itself right now, Wyatt? You got it. Excellent. And the square. We'll deal with the square in a second. Right now I just want to deal with the 1/2. How can I cancel out a 1/2? What can I do here, Caitlin? How do I cancel out a 1/2? Yes, which is the same as multiplying by 2. Nice, great math analysis there, Caitlin. So I'm going to multiply both sides by 2, and I'm going to kind of rearrange it a little bit. You'll see what I mean. So I've got V squared equals 2GH. Now how do I undo a squared, Ash? Take the square root. Brilliant. So I'm going to take the square root of both sides. So I've got this right here. V is equal to the square root of 2GH. Okay. So 2 is just a number. Do I know what the number for G is? Say yes. Yes, so I know what G is. It's okay, Jet. You can open your eyes and pretend to be excited. Good morning. Oh, hello. I have my Nerf gun. You just wanted to see if I would do it. I will. Okay. So we know what G is. We know that number is. What does H stand for, ladies and gentlemen? Height. Okay, let's go ahead and solve this problem for this particular pendulum right here. But let's make an example here. Do we need the mass of this pendulum? No. Interesting. So we'll get more into why that mass cancels out later. But just notice that we don't need the mass of the pendulum. Interesting. Okay, we need a brilliant measuring person to come up here. Eliana, I need your support. I need you to use this meter stick, and we will measure this pendulum. So it's a bit tricky to measure. I might need 2 meter sticks. Eli, come here, I need your help. All right, so you hold the meter stick. So this is the lowest point in the pendulum. Eli, I need you to mark the lowest point in the pendulum right here. Go ahead, with your hand or something. I promise not to drop it on you. Okay, something like that. Okay, now I'm going to hold this right here. Now, Eliana, what we need is the difference between Eli's finger and where it is now. So how do you think we can best measure this? Well, we need the height though, so in the Y direction. So Eli, maybe if you can keep your finger at that height, but shuffle over here. Okay, Eliana, so measure from Eli's fingertip to this pendulum right here. 40 centimeters. Brilliant. All right. So let's go ahead and convert that to meters. Great measuring and support there, ladies and gentlemen. So let's go ahead and calculate this. We've got B equals square root 2. What is the number for G, ladies and gentlemen? Remind me one more time. Ready, go.
9.81 meters.
Good job, man. Everyone named Eli. What is the variable, or I'm sorry, the number for everyone except Eli because he already did it. What's the number here, everybody? The units and everything. Great job. Meters per second squared. And Eliana, what did you measure for the height? 40 centimeters. Let's convert that to meters. How do we convert? We got to divide by 100, so move the decimal 2 times. What do we get here, Ash? For 0 meters. Excellent. Okay. Now be very careful when you calculate this. I recommend that you do all the multiplication first, and then hit equals, and then take the square root. But you can do it all in one step if you want. Where'd my other projectile go? Ha! I found it. Ash was stealing. Jeez, Ash. Steal my toys. Gosh, it is a million degrees in here. It's usually very How's that calculator going? Give me a thumbs up when you think you got an answer. Once you got an answer, check with your neighbors, see if they got the same one. Make sure they took the square root, they multiplied everything. Your invisible neighbor did very well. You may congratulate them. High five your invisible neighbors. You're a crazy person. Okay, what did you calculate here for the velocity of this pendulum at the bottom of its swing, Brianna? With the units and everything, raise your hand if you got that same number, 2.8 meters per second. Excellent job, ladies and gentlemen. 2.8 meters per second. It's like challenge teaching. Okay, so what do you think? Conservation of energy problems. Terrible, awful, difficult? Not so terrible. So I'm going to hand out your homework. Most of the problems are going to be similar to yesterday's, where you're calculating kinetic and potential energies for various scenarios. There might be a couple more things. There's going to be 1 or 2 conservation of energy problems. I want you to at least try the one with the pendulum. If you get stuck, I'd be happy to support you. But you work through this, you have it in your notes. It'll be the same process with just slightly different numbers. So, great job. Any lingering questions while I collect your homework to be handed out? All right. You got about a little more than 10 minutes to get a solid head start on here. Now don't look at that pendulum too much or it's going to hypnotize you. What's up, Ariana?
In the homework, will we ever have to use a different, energy?
Yes, but not today. I have an Nerf gun. It doesn't hurt, but it'll startle you. You will do all of your homework. You will put your name on your homework. You will remember to square anything that needs to be squared. You will put units with all your answers. Is it working? Okay, good. Okay. Good choice, fish and pencil marks. Do you have the yellow highlighters to match the yellow homework to take you? Oh, okay, good. Yes, ma'am. The total energy, yes. Right there. Oh, yeah, sorry. See, you cruising through these problems, huh? Smarty. Are you able to catch up on the notes there, Tyson? Let me know if you have questions, okay? pendulum problem on the backside first, while it's all fresh in my mind, because it's a bit more difficult than some of the other problems. Go ahead and work through that problem exactly the same way we did it. Okay. Do you want to paint it?
Can you see you without your glasses? You're gonna be like, yes, crazy woman.
I'm not that smart.
Oh, okay. Sometimes it's like when cause I wear contacts, sometimes it's easier to take your glasses off your homework so you're not like in that weird part at the bottom of your glasses. I got you.
Matthew's just a perseverer. It's energy. Fair enough. I suppose you could sacrifice the pendulum. Okay. So you remember where we went from here? Okay, great, very good. Oh, questions, great. I'll be there in just a sec, Ariana.
So this one, I have
Well, that makes sense because you've got 2 times a half, so it just cancels out to 1. But you're gonna take the square root of that, right?
yeah, it's big for
Okay, great. Carry on. How you doing, Ariana? Oh, okay. Well, let's work through the problem the way that we did it on the board. So you kind of skipped right to this statement right here, but it's really important that we work through it all the way. I know it seems tedious. We'll be able to skip steps later, but for now we need to work through each step. So first go back and work through this one that we did on the board, and then I'll come back and support you with the grades, okay? Yes, ma'am. Sure. So let's define the beginning and the end of the problem. What is the beginning of the problem? Where it starts, at the top of the hill. Okay. Ooh, this one's complicated. Let's save this one and we're gonna work through it together tomorrow, okay? So, ladies and gentlemen, go ahead and save problem number 8. We'll work through it together tomorrow. Maybe like circle it. That'll be our do now for tomorrow. Yes, sir. Okay, we did this exact problem in our notes. So just work through it the way that we started. So I want you to work through it exactly the same way that we did in our notes, okay? Yes. Yes. Nice work, Lauren. It's very thorough, showing all your work there. Well done.
You do have a highlighter to match your homework. Oh man, that's great.
Boxing your answers, putting units with your answers. Well done. Great work. So eventually we will be able to skip right from here to here, but in the meantime, I do want you to write that in it's hard. How you doing here, Libby? Good. Anything I can support you with? Okay, let me know if anything comes up. I'm sure you get some units on there once. Yes, sir. Mhm. Well, what is that? Okay. Do you have what variable do we use to replace type? Okay, do you have it each in here? Okay, so what do you think we should do? Okay. Okay. It's working so fast. Smart physicists. She gets to be so smart. Yes, ma'am. Well, have you worked through the problem the way that we did it there? Notice how we didn't plug any numbers into it. Very end. It's okay, it's brand new, so you've done a great job start so far. So make sure that you so you started exactly where you need to, EI equals EF, saying all the energies. Now go through this list. This is the beginning of the problem, this is the end of the problem. Figure out what kind of energy it has at the beginning, what kind it has at the end, and you're gonna work through the problem exactly the same way we did on the board, okay? All right, carry on, Sally. Okay, for these problems, I need you to put the numbers in. You've written the equations, that's great. You need to substitute the numbers into the equation. Okay? All right. That way, if you accidentally, because when you're going real fast, sometimes it's easy to miss a 1/2 or miss a squared or a decimal place or something. At least I can see that you put the numbers in the right place and give you partial credit. Okay? All right, carry on, sir. Can I see? Can't show where you were. Nice. So your answers, units with everything. Nice. Well done. So this is all great, wonderful, excellent work. If you want to be even more physicist-y, that's a word, you could put the units with all these individual numbers. So you can, that's a good use of your time right now. The reason being, in the future, these equations are pretty straightforward. We're used to working with them. Later on, we're gonna get even crazier equations. And sometimes if we have no idea what's going on, we can kind of figure it out just by looking at the units. So it's just a good practice. Oh, you got your pencil here, just proceed. I'm gonna go ask you. Oh, no.